Thank you. Yeah, nice to see everyone in person. Let's see. Does this work? Yeah, so for this short 10-minute talk, I'm going to zoom in a little bit more on one of the peaks from Raman's talk, which is baryogenesis. So in particular, what mechanism generated the initial asymmetry of matter over antimatter, which we know could not have been there as an initial condition and had to be dynamically generated, and we know what it needs to be in order to explain the universe as we see it. In particular, from BBN and CMB, for consistency with those measurements, we know that the ratio of matter over antimatter in terms of yield variables has to be 10 to the minus 11th number. And in particular, Sakharov back in the 1960s told us what conditions a mechanism that successfully does baryogenesis has to satisfy. So first, there needs to be some interaction that changes baryon number. Can you do this in the standard model, you can ask? So you have these lecture weeks Aileron configurations that are active at high energy. So yes, that exists. Next, the rates for these interactions has to be different from the conjugate rate. Otherwise, you wouldn't generate an asymmetry. So the standard model has CP phases and these CKM matrix elements, but they're not large enough to generate this number. And finally, all of this has to happen out of thermal equilibrium. Otherwise, you'd wash out the interactions. And you can do that with a phase transition, for instance. The standard model has the electroweak phase transition, but you need new physics in the Higgs sector to make it first order. So the punchline is you need new physics. We've known this for many years. And in particular, there's been a large model building effort to come up with new models that satisfy these Sakharov conditions in various ways. You can add explicit B violation, you can add explicit L violation, and then transfer it to B violation through the Ailerons, for instance. So that can satisfy B violation. You can play around with different CP violating phases coming from new interactions in various different sectors. And you can consider various different ways to go out of equilibrium. And all this has led to a lot of traditional mechanisms of baryogenesis, if you will. For instance, doing it with the gut scale particles, so tying it into gut models, tying it into the electroweak scale, by adding in new physics into the Higgs sector, for instance, relating it to neutrinos and leptogenesis. And the claim for today is that these are kind of what I call these traditional mechanisms are also traditionally more challenging to test because they tend to happen at high scales, as particularly like gut baryogenesis, we know how to happen at the gut scale usually. So the standard laws, they're very difficult to test. Now, what I want to tell you about in this talk is new ideas for baryogenesis. So, there's all this work that's been done over many decades for all these kind of traditional mechanisms, but there's also been like all this new work that's been done in the last 20 years and many more. This doesn't do justice to the amount of papers that have been out about these ideas. And in particular, there's been, in my opinion, kind of an emphasis to really develop testable models that have experimental signatures. So this has been motivation for a white paper for TF08 with Julie and Shada and Bibushan, who's in the audience. And the idea is to give an overview of these new mechanisms and really an emphasis on testability. And also testability, new ideas also for testing traditional mechanisms. So in this very short talk, I will shamelessly give you an example that's one of my own mechanisms. So this is something called mesogenesis that I've been working on in the last couple of years. The way it satisfies the Sakharov conditions can be summarized as follows. We imagine we have some field, perhaps related to inflation, that decays at MeV scales. So it's a late matter dominated era, and it decays into quarks, for instance, B quarks in this case. This is below the QCD scale, so they hadronize into in this case, neutral B mesons. Neutral B mesons undergo particle-antiparticle oscillations, and that has CP violation. And it's measured by an experimental observable, so this is what experiments actually measure. This is a measure of indirect CP violation. It's related to the rate of the B meson to oscillate and then decay into some final state. So it's an experimental observable, it's measured. And then how you get baryon number violation is there's a new interaction that allows the B meson to decay into a standard model baryon and actually a dark sector particle that's charged under standard model baryon number. So this generates an equal and opposite asymmetry between the dark and visible sector. And it's controlled by this new branching fraction of this exotic decay mode of the B meson into basically a standard model baryon and missing energy. So if you do all the math and study the particle evolutions, the prediction you'll find is for this to be a successful mechanism of baryogenesis, the product of these two experimental observables has to be greater than some number. Thank you. So you can ask, is this allowed and is this testable? And it turns out this particular mechanism is indeed something that can be tested in the next couple of years. So there's a lot going on this plot. What this is the asymmetry in the B sub S and the B sub D system. This current yellow box is the limits on that. And then this red region is the value of this branching fraction for this new decay mode, such that it's big enough to generate the correct observed baryon asymmetry given a certain value of CP violation. And of course, there's some inflaton parameters that go, or some of this new particle that decays into the quark. Some of the parameters go into that, but that's very weak dependence. So now this is pretty exciting because experimentalists can go do these searches. And so, for instance, this is an example of a search that indeed, in this case, the Bell collaboration did for this model. So I said the B meson has to decay into a dark sector baryon and a visible sector baryon. It can do so, for instance, through a heavy TeV scale mediator. This looks a lot like a squark. Long story short, you can look for this branching fraction, and Bell did that, and they put an exclusion curve on it that's of order 10 to the minus 5. Okay. So actually, this particular decay channel is maybe too small to explain baryogenesis through this mechanism, but there's actually all these different other channels that this model can do baryogenesis through. And so they're planning to search for all these different operators. There's also proposed searches at LHCb, and I recently learned that Babar is also developing a search. Thank you. Yeah, so that's just one example of one class of mechanisms. There's actually many different ideas for mesogenesis now that we've been developing that utilize the CP violation in different meson systems, and they're all related to various different experimental observables. So zooming back out to the white paper, there's actually a lot of different new ideas that kind of all are exciting and related to experimental observables. For instance, Raman already told us about wimpy baryogenesis. There's ideas of connecting baryogenesis to the axion or to the QCD phase transition. This is Tim's paper. There are slightly older papers that also deal with dark sector. And then there's also all these ideas for new ways of testing leptogenesis or electroweak baryogenesis. For instance, there's ways of looking for topological defects of afflectine baryogenesis from gravitational waves. So that's also something that we're highlighting in this white paper. And I want to close by saying that this is a pretty preliminary list. And if you feel strongly that there's some mechanism that we're leaving out, there's still time to contribute. So please contact one of the editors. You can talk to me or Bibushan in person or email one of us. So that's it. Thank you.
Thank you very much. Questions? Yes, Michael.
I'm sorry, there's something I really didn't understand. So in principle, you can have a long-lived particle, boson of some kind, that decays by its own CP violation into, let's say, a quark and a dark matter particle. Okay. But why is the BB bar oscillation important for this mechanism?
Yeah,
this particle just be some very heavy particle, and
yes,
the BB bar oscillation doesn't play a role?
It can indeed, and the short answer to that is this is the first thing I worked on because it's the most testable. This thing will be excluded in the next 5 years if experimentalists continue to do the searches. Now, you could just do this with dark sector CP violation, and that's actually something that we're currently working on. But the answer to your question is this has like the smoking gun signals of baryogenesis. So it's the first thing that I want to tell experimentalists to look for.
Oh, okay.
Yeah.
Thank you.
More questions? All right. I think everybody is ready for the break. Let's thank Gilly again.